Okay, we're going to start electrical systems, and we'll start by looking at the variables associated with them. Voltage or potential uh, is recorded in volts. You should be familiar with that. Uh, Current would be measured in amperes. Then also can be concerned with charge, especially in capacitors. They're measured in coulombs. And we should note that current is the derivative with respect to time of charge. So amperes are really coulombs per second. All right. Power measured in watts. In many texts, they take note of various passive electrical elements, or including or even active ones in this way. So you may see something. I have a box here, but you can have a symbol for uh, here for resistors, capacitors, inductors, motors, and then you have a characteristic voltage drop. Here's the current approaching it. You could have a V, A, VB, V1, V2. The voltage drop as you go across this thing would then be V1 minus V2. So this is often information that's associated in a circuit diagram with an electrical element. All right. We should be aware that voltage and current for electrical elements are uh, analogous to displacement and force for mechanical elements. So if you think of a spring or a damper, changes in position drive the force through. So we have displacement, we have force. Well, in the electrical world, okay, changes in voltage drive current. So force and current are analogs, as are displacement and voltage. Okay. Uh, the passive elements, you should all be fairly familiar with them. The resistors, uh, they go by V equals Ri for linear resistors. There are nonlinear resistors. We're not concerned with them. R is measured in resistance. Power dissipated, obviously voltage times current, but if we insert this equation in, you can have I squared R or V squared over R. And so you can see we took this previous picture and put the usual symbol for a resistor. So you would have the characteristic resistance. This is referring to the voltage drop, and we could put a little line there for current. Anyway, capacitor, the familiar symbol for a capacitor, and we could put other information around it. But here's the equation. The current through the capacitor is C times the derivative of the voltage. So if you have a DC circuit, constant voltage here, there ain't no current going through. The current just hits a lead, boink, you'll hit a wall. Capacitance, measured in farads. Most things you handle by hand will probably be measured in microfarads. Okay, a farad's a pretty serious unit. If you have something that's a farad size capacitor, and it's been fully charged, and you put your fingers across the conductors, it's going to hurt. So that's why if you handle a capacitor, you want to make sure that it has been discharged, because you can get quite a little shock from them and burn. Where does capacitance come from? And in terms of the components of computing this, you have the permittivity of the dielectric material between the plates. So that'd be the stuff in here. You have the distance between the plates is a factor, and then the area, cross-sectional area of the plates. All right, so epsilon A over D capacitance. All right, and as I just mentioned, C is often expressed in microfarads. So if you're looking at a typical circuit, if you're looking at a computer board and you have capacitors and stuff, they're probably down in that range. Capacitors store energy, and the energy stored is 1/2 CV squared. All right. And we have one other element we need to add in there. That's the inductor. So here's the familiar. This is, kind of looks almost a little springy, but the voltage across the inductor is L di dt. So the only way voltage goes through you have a voltage across this thing as if there's variations in the current. So that's kind of interesting. Uh, this stores energy in its magnetic field as opposed to the electrical field, and the energy stored is 1/2 Li squared. All right. So let's see here. We will be dealing with sources. There's the ideal voltage source that simply current is coming through and it takes the voltage and steps it up. And you can have an ideal current that just creates a current and sends it on its way. So people have voltage current supplies, boxes that sit on their tables there. Voltage, a constant voltage battery, a symbol for that. So again, this would be DC, and it steps up the voltage as you go across the battery. Non-ideal sources, the source will have some characteristic resistance, which means it'll eat some of that voltage. So here's something to step up the voltage, and then a little resistance to reflect the non-ideal element. For current sources, we would have this R in parallel. Okay, so then it just releases a current, little leaks out, you have this voltage drop, and then it comes back. We can have an open circuit. That means no current flows. A closed circuit means it does flow. There are two critical laws that are commonly used when analyzing circuits and systems. We have Kirchhoff's voltage law, which says in any loop, the sum of the voltages is 0, and Kirchhoff's current law, which says at any node, the sum of the currents are 0. Let's take a little deeper look at them. I'll do that right here. So if we have let's say, here's ground, resistor, capacitor, inductor, and all of these could go off to other circuit stuff. So I'm just looking at this loop, R, C, L. All right. So as I go across here, so ground, that's 0 volts. So if I were to say the voltage across here, call that VR, going around, and then the voltage going this way across here, C, VC, plus the voltage across here, VL. Well, I know when I get back over here, the voltage is 0. I started at 0, I'm ending at 0. I mean, somewhere in here, there's voltages going down or voltages going up, what have you. Okay, but in any loop, if you sum the voltages of all the elements, it has to be 0. Okay. Now we have the other Kirchhoff law, which says at a node, current sums to 0. Well, so I have let's say a circuit like this. So here's a node, and so we can have resistors, capacitors, voltage sources, motors, same here. But I have some current coming in. All right. Well, and then I'll assume there's current going out, IB, and current going out, IC. The sum of all the currents here coming in and going out must equal 0. It's that simple. You can't, within the node, you can't be storing current or throwing it out, dumping it. All right. All the currents at this node must sum to 0. And it's basically, you can look at that as a conservation of mass kind of a thing. Mass in, mass out has to sum to 0. In this case, there's no room for current or no mass to be stored. All right. So those are the Kirchhoff laws. And so let's go down to do a little comparison here of electrical and mechanical elements. And so you are familiar with force is equal to ma. Well, we can write that as mv dot, and I'm putting a bar over it to emphasize the vector and velocity as opposed to voltage, which is also v. So when I put the bar over it, I'm just trying to emphasize velocity. On a damper, force equals B times, quite frankly, V. So you're used to that. And force equals K times X. Well, notice if I was to integrate, or no, not integrate, if I take the derivative of that position, I'd get velocity, and that will put an F dot here. So I can relate everything in terms of uh, velocity and force. Okay? Well, let's take a look. Uh, so here we have. All right, I'm going over my notes, and I had a comment in here, and I have no idea what I was thinking of when I wrote that, where I wanted to go with that, so I just got rid of it. So excuse me for the short interruption. Uh, let's take a look at a resistor. The current I can write as 1 over R times voltage. Force equals damping times velocity. 1 over R is analogous to damping. Okay, so we want to start, I just want to show the analogs between electrical and mechanical systems. A capacitor, current equals C V dot. Okay, a spring, or no, mass equals M V dot. All right, so capacitor is analogous to mass. Okay, an inductor, I dot equals 1 over L V. A spring, the derivative of the force equals kV. So 1 over L is analogous to K. All right, so I had mentioned previously the analogy between electrical and mechanical systems, so we've shown that. A couple more issues, things that you're hopefully familiar with. Resistors in series add. So I have one resistor after another. That's just, I can replace them by one resistor, which is R1 plus R2. Okay. Also, hopefully you are familiar with resistors in parallel. We can replace all them with one equivalent resistor. So V equals R equivalent IT. Well, how do you compute what that is? Well, the total current going through here, so the voltage across here, we can use Kirchhoff. This voltage has to equal that voltage because I can do a loop. This voltage has to equal that voltage. So they're all the same voltages. So the total current will be whatever this voltage is across all three, divided by R1, divided by R2, and divided by R3. This would be the total current going through. And I can factor out the V, and I have this. Well, if I divide that out to the other side, I get voltage equals R equivalent times I. So it's 1 over the sum of 1 over all of the resistances. A little bit of a nightmare to compute, but a simple equation. And hopefully you are all familiar with that. And with that, our introduction into electrical elements is over. And I will see you again as we start moving into some problems. Bye for now.